Good afternoon and welcome to this tutorial in which we are going to run this example, an infinite array of collinear cracks using an Abaqus UEL user element subroutine, and for the purpose of this tutorial is going to be a real valued UEL. So this is the problem, and due to the multiple symmetry conditions of this case, this is the subdomain that we are going to create in our finite element discretization. It has a symmetry with respect to the x-axis and both symmetry conditions in the y-axis. We are going to see those symmetries later defined in the input file. So the first thing that I'm going to do in order to run this example is that I'm just going to go to the supercomputer that we have in here in UTSA. It's called Shamu, and that's how I log in Shamu. I'm going to ask for my password. And now we are in the main node of Shamu. I'm not able to run in that node, but I have access to a specific node in which we are going to be running this example. So I'm just going to type module load sge q login minus q millwater.q. That's the node that we have access here in the lab. And right now we are in the compute node 005. That's Millwater's node. In here, in this window, I have a direct access to Shamu in my local machine. So if I go here, this is my main directory in Shamu. So we are gonna go to this folder that is gonna be called benchmark problems. It's going to be a 2D elastic, and the problem that we are going to be running is the infinite array of cracks. And we are going to be running the real UEL. So those are the files. Let me erase these ones. Those come from a previous simulation. So we start from the beginning. So those are the needed files in order to run this example. I'm going to change directory here in the terminal. So I'm just going to go to benchmark problems. It's a 2D elastic is the infinite array of cracks, and we are going to be running the real UEL. So we can see here 5 files, the same ones that we have here in this window. Okay, so let me walk you through each one of these files. So the first one is going to be the Fortran code, which is the regular 2D elastic finite element code, but it's at an element level. So what we are going to have to give Abaqus at the end of this subroutine is going to be the stiffness matrix and a right-hand side. Then Abaqus is going to take care of the assembly of this elemental stiffness and right-hand side vectors, stiffness matrix, and it's going to take care of the assembly and the solution of the system of equations. Here I can define elemental output variables. So for the purpose of this tutorial, we are defining in the S-bar number 1 the strain energy that is computed as the half of the displacement times the stiffness matrix times the displacement vector. So that's how we compute the strain energy in a linear elastic body without tractions in the crack surface. The next file that we have here is the Abaqus v6.env. So that's an Abaqus environment file that is going to allow the user to write the UEL that we just showed here in Abaqus free format. So as you can see here, this is a free format Abaqus UEL file. So this is what that file allows us, only to write in free format. So important as well. And this infinite array of cracks.imp is the Abaqus input file. So here's how I call my model, and it's going to be a user element, and the type of the element is going to be U1 that corresponds to user defined. I'm going to have A nodes in every element of the domain and 2 coordinates. This is a 2D example, so it's going to be X and Y. I only have one variable defining here. Remember that I'm only defining the strain energy. So for each element of the domain, we are going to have an elemental strain energy. And these 1 and 2 are the active degrees of freedom in the UEL. So for this case, it's going to be the X and the Y displacement. So here we have the nodes. So node number 1 is in the 0, 0 coordinates. Node number 2 is in the 100 and 0 coordinates, etc. And we have a total of 79,105 elements. And for those, nodes. And for those nodes, I'm gonna create a node set called all. So if I'm gonna refer to that node set later in this input file, or I'm gonna request an output such as displacements associated to this node set, I'm gonna refer to it as all, which are all the nodes in the domain. Then we have the element definitions. So we have the U1, which is the basic user-defined element, and I'm calling all the elements in the domain under this alias, which is an all E. That's how I'm gonna refer to all the elements in the domain. So here we have the element ID, and then all the 8 nodes associated to that element. Let's go almost to the end of the file. And now here we can see that we have a total of 26,112 elements. Then we have some node set definitions. This is going to be dir1, which stands for dir-elect 0. Then we have a dir-elect 1, and then we have a node set called dir2. Those are associated with the boundary conditions that we are going to be showing later. Then we have the UEL properties, and for the purpose of this example, we are gonna care about these 2 properties that are the elastic modulus and the Poisson ratio. All the other properties are not important for this simulation. Then we have here the boundary conditions. So in the dir-elect 0 node set, we are going to be restricting the movement in the y direction. So based on this subdomain, we can see that that node set are all the nodes that are here. Then dir-elect 1 and dir-elect 2, we are restricting the movement in the x direction. So because of the symmetry, those node sets are this one and this one to the right. So it's the left and right symmetry conditions. Then we have the concentrated loads, which are applied here. So we have a surface traction of 1 megapascal, which is going to be then divided into each of the nodes here in this top surface. So here we have the x loads. So for example, here is in the node 453, in the x direction, we have a load of 0. That's obvious because the load is only being applied in the y direction. But then, if we go to that same node, 453, but now in the y direction, which is in the index number 2, we have a concentrated load of 104. So we do that for all the nodes in that subsurface of the subdomain. Then here, before we end the step, we are going to ask for the outputs. So for the first simulation that we are going to run, I'm going to uncomment this, and we are going to have a node print. So we are going to request a nodal output for the node set called all, so corresponding to all the nodes in the domain, and I'm going to output the x and the y displacements that are called U1 and U2 here in the Abaqus syntax. How am I going to run that? We have here a bash script with a job name, the UEL file. Then we call here the Intel and Abaqus modules within Shamu in order to first compile the UEL and then run with Abaqus. We are defining a temporary folder in order to store all the runtime files. And then this is how we call Abaqus. So we are going to call Abaqus, job equal job name, so it's gonna be this job name. Then we have our input file that we just defined in here, and the user element that we are gonna be using is this 2D elastic reel. And that's it for the shell file. So if I go here to the terminal and I type run real uel.sh and I hit enter, we start the simulation. So it's gonna take about 10 or 15 seconds in order to run this example. So it just finished, and it created a bunch of files, but the one that we are interested in right now is this infinite array of cracks.dat. If we see that file, what it's giving us is that for these nodes that are the 1, 3, 4, 5, and all the other nodes in the domain, is giving us the U1 and U2 degrees of freedom that are the X and the Y displacements associated to that node. Here in the provided files, we also have a reference displacement obtained from another Abaqus simulation. And if we verify, we can see that the values are in total agreement. So the UL that we just ran with the input file and the Fortran code that we just used is good. So this is only for verification purposes. Now, if I am not interested in the nodal displacements, but I'm interested like what's the strain energy for each element in the domain, I'm gonna go ahead and comment those two, and I'm gonna uncomment these two lines. So we are gonna have now an elemental output associated to the elemental set called OE, which remember that are all the elements in the domain, and the variable that we are gonna request is the number 1. Now, remember that that variable was the strain energy that we can compute it here using this mathematical formula. So now let's go ahead and run the UEL again. It's going to ask me if I want to overwrite the file. I'm going to type Y, and it's running. It takes the same amount of time. So it just finished. And if I go here to the infinite array of cracks, which is the job name that we define here, all the output files that Abaqus is gonna give us are with the job name, are using the job name that we define here. So if I open that file, now we see that there's an SDV1, and it's gonna give us the elemental value of that variable. So we computed the strain energy for each element, as we show here in the Fortran code, which is an UEL, that is user element subroutine, so it's user based. So for each element in the domain, we are computing what the strain energy is. So those are the strain energies. So it's giving me the strain energy for each element in the domain, and then we have a maximum, a minimum, and a total of the strain energy. And that's it for this tutorial.